action. Hello and welcome back to Calculus 1 section 4.1 on minimum maximum of a function. These are called extreme points. We're going to define few things here and use the derivative. So entire chapter 4 is application of derivatives. So we'll be taking a lot of derivatives obviously for each problem, and today we are going to put together some of those concepts from before. So if you observe, red, why? Come on. If you observe some kind of a curve function f of x, you will see that there is a horizontal tangency at a point slope m equals 0, and then on the bottom as well we can find horizontal tangency m equals 0 where the slope is equal to 0. Now that occurs when you have max and a min. Just leave some space between min and the line. We'll fill in the blanks. So what is happening here? Well, we have a derivative, right? And we know that the derivative computed at a point is going to give us a slope m when we talk about tangent lines. So on this graph, it looks like that we can find the derivative of a function, set it equal to 0 to force the horizontal tangency, and then simply force horizontal tangency, and then find that way x's at which that occurs. So we have, before we go into calculating all of these, let's first figure out what are the types of min and max that we have. So here is the function f of x, and we see two max values, and they have they're categorized into different groups. The one that it's higher, the highest of all max values, is called absolute or global max. So that one would be, well, we'll talk about that. And then you have the other one, which is called relative, also known as local max. So you have relative max and absolute max, or you can use the words local and global. Now, every time you have min or a max point, you're having some ordered pair xy. And for maximum to be absolute maximum, the y value has to be absolutely highest y value of all points in a domain. So this y value is the highest y in the entire domain. It's the highest value on the entire domain. A relative max or a local max is a boss in its own neighborhood. So you can think of a president of the country and the governor of a state. All right? Or you can think of governor of New Jersey and a mayor of a town. All right? So mayor is a boss in a town, right? But the governor is the bigger boss, right? So both of these values are max values, except this is the absolutely highest y point on the entire function, and this one is the highest y point in the neighborhood. Now, we also see a minimum value here. What kind of minimum is this?
Global min.
Global?
Yeah, it's the smallest of it, right?
Well, now she said local. Why local? Because there are lower points, yes. Local or relative. Look, would you agree that this point over here has a lower y value? In order to be absolute or global, has to be the minimum value and no other point will go below ever. X squared. This is a global, right? Global min. Because never will these turn back down to have a lower point. So that's what it means to have a global min or a global max. So absolutely lowest y point. So now we have the vocabulary of global or absolute, min or max, and then relative or local, right in its own neighborhood. The next is for us to define something that is called the critical point, because these min and max values will occur at those critical points. So, definition of a critical point. An interior point C of the domain of function f of x at which, number one, the derivative of that c is equal to 0, or number two, the derivative at that c does not exist, is called a critical point of f of x. So that's what we have. Now, this critical point, now let's go this way. This critical point could be min, could be max, or could be something that we haven't seen yet. So stay tuned. It's called inflection point. So now let's take a look at this in practice, right, with the function problem that we are familiar with, that we actually don't need to use calculus to know the answer. What do we know about function f of x equals x squared? What does it have? It has a global min, right? You know what the graph looks like. You know it has a global mean at 0, 0, and you're just done, right? But let's use calculus to verify this result. So critical point is going to be when we take the derivative of x and set it equal to 0. So the derivative of x squared is 2x, and we set it equal to 0, divide both sides by 2, and we get that x equals a 0. Now, this is called critical number. Because it's only x coordinate, right? Only x. Now, we are going to find the y value. Well, let's put it this way. Y equals f of 0, which is 0 squared, which is 0. And now I have 0, 0, and this is critical point. This is critical point. So what do I have for the critical point? I have 0, 0. Now I need to know if this 0, 0 is a min or a max. And the way to answer that is simply to calculate 2 points, one to the left, one to the right, and then just take a look at the values. So we know critical point is 0, 0. So now I'm going to find f at -1, which is -1 squared, which is 1. So I have -1, 1 as a point. And I'm going to calculate f at 1. So I'm just going to say test min max. Okay? Test min max. And then it's 1 squared, which is 1. So I have 1, 1. So look what we have. We have -1, 1. We have 0, 0, and 1, 1. We know that the graph goes through this. So it's clearly a minimum. Because the y value is lower than the two values that we calculated to the left and to the right. So it has to be a minimum. And that should make sense. So we say it's a global or absolute minimum. Whatever word you use, right? I gave you both because different books use different words. So whatever you see in a book, in a homework, you know what it means, right? Global and absolute is the same. And then local and relative is the same. So that takes care of this situation. Then we take a look at, let's say, f of x equals e to the x. So we take the derivative of e to the x, which is e to the x, and set it equal to 0. What do we get? We get no solution, right? Because if you ln both sides, you get x equal ln 0. Ln 0 is negative infinity. So there is no solution here. No solution means no critical point, which means no min max. And you know that, because when you graph e to the x, goes through 1, this one goes up forever, this one goes down forever towards 0, but it never reaches it. So there are no min and max on e to the x. And now I want to take a look at f of x equals x cubed. What's the derivative? And when I set it equal to 0, what do I get? Yes. So when I divide 0 by 3, I get 0. Square root of 0 is 0. So it seems that I have critical number. Then, to find y value, I plug in critical number into original function. I get 0 cubed, which is 0, which gives me 0, 0 critical point. And now we do the min-max test by calculating f of -1, which is -1 cubed, which is -1. And then I calculate 1, which is 1 cubed, which is 1. Uh-oh. Do we all see the issue? On our graph, I have -1, 0, +1. Yeah, but in order for the middle point to be a min or a max, the other opposite points have to be both up or both down, right? Because in order for it to be min, you have to have both up. For this one to be min, to be max, these both have to be down in order for the middle one to be a max. Now you have one down, one up. This is that third case that I said, yeah, in the inflection point. So no min, no max, and this point is this point is what we call inflection point, and that's coming up next weekend, right? So we have a procedure which is very simple. Take the derivative, set it equal to 0. Now, what kind of functions you have? Now you're going to have product rule, quotient rule, chain rule, implicit differentiation. You're going to have all different types of derivatives to take because you learned all of that stuff in chapter 3. So this is the reason why we were practicing simplifying functions so that we can solve these equations quickly and get critical points which turned out to be min, max, or as we can see in this particular example, inflection, but that's for later. So let's take a look at some of the homework calculations where they give you interesting stuff to solve. For instance, well, let's start with, vanilla exercises like 27. F of x equals 3x cubed plus 3/2 x squared minus 2x. Find the derivative, set it equal to 0, and go from there. All right, let's take a look. So the derivative here is 3 times 3, 9x squared, plus 2 drops, that's 3x, minus 2. We set this equal to 0, and then solve. It's quadratic, so we have to factor this, if possible. Or you can use quadratic equation, whatever you like. We can go and work with factors of negative 18, which is 1 and 18, 2 and 9, and 3 and 6. So it's positive 6 and negative 3. So we have 9x squared minus 3x plus 6x minus 2. Then factor out 3x, left x minus 1. Factor out positive 2, you're left with, it's 3x, there we go, 3x minus 1. And then 3x minus 1, 3x plus 2, equal to 0. So we have 1/3 and negative 2/3. So those are your critical numbers. Which are only x values. And then you find the y values by plugging in these in the original problem. So that's 3 times 1/3 cubed plus 3/2 times 1/3 squared minus 2 times 1/3. Work out some fractions. 3 will kill one of these, so you just get 1/9. Over here, 1/3 dies, so this is 1/18. And over here is negative 2/3. For the 18 as a common denominator, that's 2 plus 1 minus 6. No, 6, 12. Which is negative 1/2. Right, because that will be negative 9 over 18. So the first critical point is 1/3 negative 1/2. So we're going to box this, and now we have to do this again for the second one. So y is f of negative 2/3, which is 3 times negative 2/3 cubed plus 3/2 times negative 2/3 squared minus 2 times negative 2/3. So one of the threes dies again, so that's going to be negative 8 over one of the three is gone, so that's just 9. Square kills the negative, so that's gone, and then one of these cancels, so it's just 2/3, and then plus 4/3. This is 6/3, so negative 8/9 plus 6/3 times 3 times 3, 18 minus 10, that's 10/9. So if there are no mistakes in calculation, we have our second point to be negative 2/3 and 10/9. It's a motion tensor, so we're all way too still in the room, so it keeps tripping. So these are the critical points. Critical point and critical point. Now, if you know rules of polynomials and graphs, you don't have to calculate left or right points, you immediately know what these are. Because the cubic graph is either this way or that way from pre-calc 1. Now it's this way if a is bigger than 0, and it's this way if a is less than 0. and a is in front of the cubed term. So my a in this case is 3. So I have a equals 3, which is bigger than 0. I have this case, which means that the number that has a smaller x value, so this has to be relative max, and this one over here is relative min. Why are they relative? Because the cube graph goes up and down forever. So this one over here has higher values, right? So it can't be absolute. And the minimum over here has all the lower values on this side. So neither of them can be global or absolute. Or if you don't know any of that stuff, you just go and you compute. Now let's see some of the more fun functions, like 1 over x plus ln x. So find the derivative, set it equal to 0. So you know what to do, right? Take the derivative, set it equal to 0, solve the equation, find y values, Do we all have the same derivative?
Yes.
So now we set them equal to each other. You ship the other one with the x squared. So you have x squared is equal to 1 over x. When you cross multiply, you get x squared equals to x. And to solve this, you move x to the other side. You factor x, you get x minus 1. X equals 0, and x equals 1. Now you have to throw away the 0. Why? Why do you have to throw away 0? 1 over x cannot be exactly. So we have a vertical asymptote at x equals 0. So here, let me snake the red. So that's why we can't have vertical asymptotes. Why we can't have nice things. So now we have x equals to 1. Well, that's a good one, right? And we find the y value with f of 1, which is 1 over 1 plus ln of 1, which is 1. So 1, 1 is the critical point. And now we just need to know whether this is a min or a max. And we will have to compute this at 1/2. I mean, y is f of 1/2. So that's going to be 1 divided by 1/2 plus ln of 1/2. And then y equals, you can use 2 on the other side, so it's 1/2 plus ln 2. And then you can use your abacus to figure out these things. You have 2 plus ln of 0.5 and 0.5 plus ln of 2. So 2 plus ln of 0.5 is 1.3 about, and 0.5 plus ln of 2 is about 5.7. So clearly this is what? So what's 1, 1? It's a min, global min. Because the 2 points, if I am to graph this like this, 1, 2, 3, and let's say this is my 1, 1, then I see that I have at 1/2 I have 1, 3, so that's higher, and at 2 I have really high up on a y value. So the function is doing this. It's going to go forever up. It's going to go forever up until it hits the y axis. So this has to be a min. Okay, one more, and then we have another thing to work on. So this one is f of x is given as x squared times the square root of x plus 5. Same drill. Derivative set it equal to 0, solve the equation. Okay, no pressure, you have 15 seconds. Go. All right, so what's our derivative now?
2 over x plus 1 over 2.
I mean, what do we use?
I use ln.
We use ln?
Yeah.
Nice. You can use the product rule, but that's fine.
No, it's too much.
Okay. So you copy the whole function and then times. You did x squared, x plus 5 times, and then this is 2 over x, right? And then plus 1/2 1 over x plus 5, right? All right. You can use logarithmic differentiation, that's okay. You set this equal to 0. Now, obviously, the perks of this are you already have everything in factored form, so x squared equals 0. That gives you x equals 0. Then you have root x plus 5 equal to 0. X is negative 5. And then you have this mess of 2 over x plus 1 over 2 times x plus 5 equal to 0. Now, this one is 1 over 2x plus 5 equals to, now this goes to the other side, becomes negative 2 over x. You cross multiply, x equals negative 4 times x plus 5. And you multiply now, negative 20. Move 20 to this side, becomes negative 5x. X is negative 4. So I have x equals negative 4, negative 5, and 0. I have to find the y values. Maybe if I put them in order, huh? Put negative 5 first, then the next up is negative 4. So y is equal to f of negative 5.
Doesn't x plus 5 have to be under a root?
No, that's the half. The half kills the exponents. So f of negative 5, the original function is x squared. So that's going to be negative 5 square root of 0. So the whole thing is 0. So we have negative 5, 0. Then of negative 4, that's a negative 4 squared. Square root of 1, which is 16. So negative 4 and 16. And finally 0 is going to be 0 squared times square root of 5, which is 0. So 0, 0. So all three of these are critical points. And we don't know yet, how to work out the some of the tests that will make all of this easy. So you have to go and you have to figure out points to the left, points to the right, and all of that stuff to figure out what's min, what's max. I'll just write use left, right points on each to determine min max. Min max on closed interval. So here's the question. Does linear function y equal x plus 2? Does this function have min or max? Does it? No. Big fat no. But now, same function, y equal x plus 2. But this time, it's a line segment on interval 1 to 3. Does it have min and max? Yeah. The min is going to be at 1, 3, and the max is going to be, in this case, at 3 and 5. So I hope you will agree it's the same function. What's different? Different is that this is on the entire domain, negative infinity to positive infinity, and this one is only 1 to 3, which created these endpoints. So all of these functions that are chopped off like this, they have to have min and max. We know that x squared has no max at all, but I can quickly come up with a version of y equal x squared on, let's say, negative 2 to positive 8, and all of a sudden you still have your global min, but now you also have a global max and another local max. So this quadratic, right, x squared, we knew before it only had a global min, right? But by using these points, we were able to create global max and the relative max in addition. So now, what is the story when you have a domain that it's like this on a closed interval? Well, in addition to working out the derivative in the middle, we also have to calculate endpoints. So, when on closed interval, call it AB, in addition to working out derivative, to get critical points, we also have to compute endpoints of interval AB. So you have to compute f of A and f of B, because now they are in mix, the y values. See, earlier we just compute 0, 0 using the derivative, and that was the min. But now that I have negative 2 and negative 8, the derivative over here gives me 0, 0, and we know that's the ABS min because we did this before. So now what's new? What's new? What's new is f of negative 2, which is negative 2 squared, which is 4. So there is a negative 2, 4 point we have to worry about. And f of 8, which is 8 squared, which is 64. 8, 64. So this is what we have as new. Now, highest of all y values is going to be your absolute max, and the lowest of all y values is going to be your relative min. Or sorry, your absolute min. And everything in between is either min or a max, and it's all relative. So let's take a look at the homework examples for this. They give you a lot. Let's see, what's your favorite? You love trig anyway, so let's go with f of x equals sine 3x on the interval negative pi over 4, pi over 3. All right, so this one is fun because of the trig, right? F prime of x is equal to cosine 3 cosine 3x, and we have to set this equal to 0. So this technically means cosine 3x equal to 0, and cosine is 0. If you draw a cosine graph at pi over 2 and 3 pi over 2 and 5 pi over 2 and going on to infinity. So if I take that the 3x is equal to pi over 2, because cosine of pi over 2 would be 0, then I get x equals pi over 6. Now pi over 6 is in the interval, so that's cool. If I take 3x equals 3 pi over 2, and then I divide both sides by x, I get x equals pi over 2. Now pi over 2 is not in the interval, so we don't have to do this. Or we only have one value, so this is our critical number. Now we find the y value for it, so y is equal to original function, which is sine 3 times pi over 6, and this is sine of pi over 2, and that's 1. So my critical number is pi over 6 and 1. And now I need to know whether this is a min or a max, so I can test with oh wait, hold on, no. Now we find the endpoints. So I have negative pi over 4 to the left, so this is going to be sine of 3 times negative pi over 4, which is sine of negative 3 pi over 4. Now if you know trig, you know that sine is odd function, so minus can be kicked outside, and all I need to worry about is the sine of 3 pi over 4. Now we know that pi over 4 produces root 2 over 2, but I don't know if it's positive or negative, and I need to interact with the minus sign. So we can draw the unit circle with all students take calculus. 3 pi over 4 is there, right? 1, 2, 3. It's positive, so this remains negative. So we have one critical point over here, and then another one is negative pi over 4, negative root 2 over 2, which is another critical point in parentheses, right? And last one is y of f of, I think they said pi over 3 over there, so that's sine 3 times pi over 3, which is just sine of pi, which is 0. So this point is pi over 3 and 0. So I have 3 different points. Highest of all y values has to be your absolute max. So ABS max at pi over 6, 1, because that's the highest y value. Obviously lowest y value must be at the negative number, the only negative number you have, so absolute minimum is going to be at negative pi over 4, negative root 2 over 2. A little bit busy with trig, right? So what do we need to review? How to solve trig equations. Do they have anything else nice? Nice. F of x equals x ln x over 5 on 0.1 to 5. What? 0.1? Okay, fine. Zero point 1 you can write as 1 over 10. Okay, let's take a look at this problem together. So we have the product rule. F prime of x, copy the first and then derivative of the second. Now, the derivative of the second, that will be x over 5 times, and then 1/5 on the numerator, plus ln of x over 5 times 1, which is the derivative, set equal to 0. So fifths cancel, x's cancel, so it's 1 plus ln of x over 5 equals 0. ln of x over 5 equals -1. E both sides. We have x over 5 is equal to 1 over e. So x is 5 over e. That's your critical number. And now we take that and plug in the original problem to find y. So f of 5 over e is going to be 5 over e ln of 5 over e divided by 5. So 5's cancel, and we have 1 over e. So 5 over e ln of e to the -1. So this is just -5 over e. And we have 5 over e, -5 over e as our critical point, which can be min, which could be max. Now we calculate f of 1 over 10, that's your 0.1, which is, what was the function? 1 over 10 ln 1 over 10 over 5 over 1. This is 1 over 10 ln 1 over 50. Now if you want to be fancy, and you can, it's 1 over 10 open parenthesis ln 1 minus ln 50, and this is 0. So the whole thing is negative ln 50 over 10. So 1 over 10 negative ln 50 over 10 is another critical point. And finally we get to use the other limit, which is 5. Now that one is going to give us 0. So y equals f of 5, which is 5 times ln of 5 over 5, which is 5 times ln of 1. Now that goes to 0, so the whole thing is 0. And we have another, which is 5, 0. So there are 3 critical points. And we have this one immediately to be our absolute max, because the other two y value are negative. So this one has to be our highest. All I need to do is to compute decimals for -5 over e and negative ln 50 over 10 to see which one has the lower value to be our absolute min. So we go into the abacus and then calculate -5 divided by e, which approximately gives me -1.84. No, that's the top one. Approximately -1.84. And the second one is ln 50 close parenthesis divided by 10 -0.39. So we see that the upper value is more negative, which means that will be our ABS min. So absolutely lowest point of all the points that we calculated is that one, and it's negative, right? Negative. And then the highest is the one on the bottom, which is 0. Good. So we did a lot of examples. I just want to say one more thing, and that is, if you go back to the definition of a critical point, that was the word or. We did not see any of the problems with does not exist yet. So I'll give you an example. They're around, just they're not that frequent. So, critical point when f prime of c does not exist. Example of that would be f of x equals absolute value of x. We know that it has a global minimum at 0, 0. So global minimum at 0, 0, but it's not differentiable. So f prime at 0 does not exist. But we still have a minimum. So if you are unable to take the derivative at the point, you might have a point. You have to check. Also, not to be confused with vertical asymptotes. You cannot have a point along vertical asymptote. So if you look at the theory, you have y equal f of x, and you find f prime of x does not exist at x equals, let's say, some value c, there are two possibilities. One possibility is a point, in which case it goes to critical point and you have to assess min-max. Or it could be vertical asymptote. In which case, no critical point. And that should be common sense, because you can't have point on the vertical asymptote. Functions cannot touch, cross vertical asymptote. So when you have that the derivative does not exist at the point, well, if the point actually exists, like in our absolute value case, which I showed you earlier, then that will be your min or a max, depending on what your test gives you. And but it could also be a vertical asymptote, like 1 over x. 1 over x is not differentiable at 0, because the derivative of 1 over x is negative 1 over x squared. So vertical asymptote is preserved at the same location, and you still are not able to calculate y value. So that's it. I hope you are not disappointed with this lecture. Next lecture is very short, so we're going to take a break and walk, go outside, get some fresh air, come back, and work on 4.2.